A stress-strain curve is very similar to a force versus extension graph. Strain is the change in length of a material compared to its original length when a force is applied. This is similar to extension. Stress is a force applied over a certain area. This is similar to the force axis. The values of the stress-strain curve are discussed in the next section, Young's modulus, but for now we can discuss some general principles of this stress-strain curve and what it tells us about a material. The stress-strain curve plots the stress values, force over area, along the y-axis, and the strain values, extension over length, along the x-axis. As force applied to the material increases, the stress it is subjecting to increases proportionally. As long as the shape and width of the material do not change, the force applied and the stress felt will be linked. As soon as the shape of the material begins to deform, the stress and force take on different relationships. This occurs when the object is no longer elastic, but plastic. As the force is increased, the length of the material increases, so extension and force are proportional. Once the shape of the material changes, the increase in force has a different, non-proportional effect on the increase in length. Again, this occurs in the plastic region of our graph. We can therefore see that the area of our graph of stress versus strain, which increases linearly, obeys Hooke's law and behaves as an elastic material. A stiffer material will undergo less extension when exposed to a force, and so will have a steeper gradient on a stress-strain graph than one that extends more under stress. Materials with a high gradient on a stress-strain graph tend to be brittle. Once they have reached their elastic limit, they will not often go beyond before they break. When they break, this point is called their breaking point. For a less stiff material with a lower gradient, there tends to be a much longer period of plastic behaviour. Here, the material reaches its elastic limit, or point of proportionality, and then the applied force creates a much longer extension of the material. When a force applied generates a non-proportional extension, the material is said to be plastic. Materials with a lower gradient tend to be softer and have a longer plastic period before eventually breaking at a greater length. Materials can also behave differently to application of force and withdrawal of force. When you apply a force to a material, you cause it to stretch. This stretch puts energy into the bonds between molecules and atoms within that material. As you increase the loading force, you uniformly increase the energy going into a material. When you take off the force from the material, this energy is released again. If there was 100% efficiency in these energy transfers to and from the bonds within materials, then we would expect to see a curve for application of force to be identical to the curve for withdrawal of force. We know from our discussion of efficiency in the work, energy and power section that transfers of energy are not 100% efficient. So we should expect to see that the energy going into stretching the material is more than the energy that comes out of the material when we remove the force. What this means is that the graph for application of force looks similar but different to the graph for withdrawal of force. The withdrawal curve is lower than the application curve. As long as the elastic limit has not been exceeded, the material will return to its original length. It will do so by a route of lower energy though.